Okay. I have your exams. I'll hand them back at the end. I did update the answer key that's online. There were 2 typos. One which was caught immediately after I posted it, apparently. And then there was another one that I caught later on. So it's there. You can take a look at your exams, take a look at the answer key. If you have any questions, email me or come see me. You can check the math. If you see any discrepancy, let me know on that as well. I was kind of in hyperspeed mode to get them done for today. So final exam is next, for you guys, it's next Friday morning at 8 in this room. Right, we don't change rooms. I had to explain that to freshmen this morning because they didn't know where their final was. I said it's in the room unless it's a lab, but they knew that. And it will be multiple choice, but it'll be my multiple choice. A good preparation for it would be to look at the problems that are in the last folder. There's 80 some multiple, or I don't know, there's 70 some multiple choice questions there that I've written as review. The first 5 are from next semester. So if you're looking at them going, I don't know how to do those problems, you don't, because you haven't taken second semester yet. But there's some there to take a look at. Next semester is the ACS written final, but this semester is mine. So that would be a good try. There are study guide multiple choice questions over in the library on 2-hour reserve. And then there's always the end of chapter problems in Top Hat, which I know don't necessarily match up per se, but they're additional problems. So you have more problems than I think you would do, but I would look at mine first, then I would go mine first, then I would go after that to maybe ACS or Top Hat, either one. The Top Hat problems should all be done by, including chapter 18, should all be done by the final. So on the final day, on finals, I will go through and add in the Top Hat scores, which may or may not boost your overall score, because if you have a high percentage now, like 100%, then hopefully you have 100% at the end of it, of doing those problems. So if you have to do 3 chapters worth of problems this weekend, I guess that'll be good review. But we'll try and narrow that deadline window next semester. Yes.
For Top Hat, you grade for completion, not correction.
Right. Yeah. And you're going to get out of that what you've put into it, right? So if you're just going to randomly start click no, click oh, yes, move on, you're not going to get much out of it. And maybe that's your goal at this point, but I mean, anything, those will help you if nothing else. And if you have questions, I'll probably be answering Piazza questions from now until next Friday. So post them up there and I will get to them. Hopefully I'll have everything cleared by the end of the day, each day. So, or come and see me, either way. The resumes. So I will get a final list of completed resumes and cover letters next Wednesday is when they're going to give it to me. If I know you have to go talk to a peer advisor, you got an email after class on Wednesday because they sensed that people were confused. And they were supposed to take care of this for me. That was part of the selling point, was you don't have to do anything. Okay. Well, that's not necessarily working out that way. But if you've made an appointment, got things approved, great. I would like you to try and do that if at all possible. But if it's just not going to happen, send me a copy of the resume or the cover letter so at least I know you've worked on it. So that way I may put into I may put into if you have me next semester, I may put that as a assignment that then you already have it done. Because if you're chem or bio, that's going to be required. I think, I'm not sure what the other majors are requiring, but I know cover letters and resume. If you get your resume up to date, then you'll be in good shape for internships in the spring. For the career fair, that's like the first month in February. I think there's a career fair, so you'll have everything ready to go. But if you want, you can send it to me, then I'll give you credit for it. And then next semester, you can go ahead and put it online and go through that process. There'll probably be LinkedIn will probably be my assignment for next semester, to get the LinkedIn done as well. So, other than that, you got a link, I guess, for the course evaluations. You should have gotten an email with a link on that you can fill out. And please do that. That's how you give me feedback on what I need to take a look at, change, what you thought was effective, what you would like to see more of. So that's important to fill out, and that'll stay open whenever it stays open till it's open till next week. I'm not sure what Todd put down, so I don't have any control over that. That comes, it opens up and then it disappears, and then whenever grades are due, which are now January 2nd, after that they'll send me a report. And what I will do, since grades aren't due until January 2nd, the grades will be done before I leave. So they will be online. I'll send an email out when the final grades are done on Canvas. And so you'll be able to see what grade you got. And then I will probably fill those out a couple days later, just in case there's any numerical protestations you want to make. Notice I put the word numerical in front of that. So if I made a mistake somewhere along the line, then I'll take those into account. But at some point they'll go on, because they will roll the grades, or they'll process the grades the morning of January 2nd is the plan. So, and then hopefully we won't ever have finals like right before Christmas Eve again, because I think that created a lot of problems, and the president giving everybody Monday off created probably a mini crisis somewhere, because then they couldn't roll the grades on Monday night and get them all taken care of. Whatever. Okay. All right. Do you have any questions about format, final, non-content questions, Sarah? Yes. There are some additional naming problems in that final folder. You will get to use that. You got to use it on the exam. You'll get to use it again. I'm just trying to remember if I included that last year in their final, but I will include it. You'll have a periodic table. You'll have that. You'll have the selectivities of the stuff we've been doing. I think that's all of the things you'll get. You will not get a table of addition reactions. You'll still have to know that.
How many questions will there be?
Let's say 75-ish, 75 to 80-ish. Tommy?
Well, you said we'll get the selectivity thing?
You'll get the selectivity percentages, yeah.
Oh.
Or the selectivity is like the 1700 to 80 to 1, and the 5 to 3.4 to 1, and the 1 to 1 to 1. You'll get that. Julia?
What kinds of questions do you anticipate being, all multiple choice, or will it be like a few open-ended, or?
Be all multiple choice. And it will be very similar types of questions, not exactly the same, but the same general questions that you see on those practice problems that are in the final folder, because that's the way I write questions. So will you, if you go through the topics, somebody's asked, like, what do students, this is a massive amount of material. It's not as massive as it's going to be next semester, but it is a large amount of material. How do you organize it? And one of the things to organize it would be to go back through either for each exam, or you could go chapter by chapter and sort of create what's the list of topics that I need to know for that. I tend to tell people to work backwards, because at this point, hopefully if you looked at a Lewis dot structure, you'd be like, oh, that's a piece of cake, right? And hopefully that's the way it should be. The newer stuff, you'd want to go through the exam, make sure you've got that under control. There are some free radical halogenation problems in the chapter. If there's alkyne problems, we didn't do that. There very well may be some alkynes in that final folder. So you want to kind of organize it. You could organize it according to topic, like RNS, different types of stereoisomers. The alkene reactions are kind of organized, hopefully, within the chart. What's regio, what's stereoselective. They specifically, like, what do students find effective for organization? So I asked a couple of TAs yesterday, and they said they would go through for each exam and sort of make a list of topics. I looked through my iPad to see if I did that for the summer students. Some of them were quite needy. But I did it for second semester. I don't think I did it for first semester, but if I get time, maybe I'll go through and put together a list of topics. But I can't guarantee that I'll do that, but I'll try. And maybe I'll send it out and put a post online. But you, again, this is one of these things, as you go through your notes or as you go through the book, if there's something that you look at and you go, oh, that doesn't quite make sense, then it's something you need to look at. Just like if you're doing the problems. If you're doing the problems and you're like, I don't know how to do this problem, then maybe that's something to look up. So, I mean, it's going to be review, and it's equally spaced. I don't think I put any emphasis on any one material on the exam. So it's not like I hit alkenes hard or I hit RNS hard. I think it's a broad across all the topics and probably hit all of them at least once. You may think otherwise when you take it, but I tried to make it sort of over all the different topics. So I think organizing what you need to know would be the first step. And then looking at those problems as a way to guide you as to, okay, I remember how to do this, I don't remember how to do that, would be the way to go. I would think, but again, it's going to depend on what your organization is, if any. What else? Christian?
Do we use a calculator?
If you need a calculator to do these selectivity problems, you can use a calculator. There's no other problems, I think, where you need to do any math. What else? Joey?
How much, like on average, does this usually affect people's grades?
Well, so on the syllabus, this exam counts as another exam.
Okay.
So I think they were 3 exams at 20% each. And then the final exam at 20% each, and then 20% comes from the problems and the graded problems. Come from the top hat problems, the graded problem, and then 1% each from the resume and the thing. So what happens is I haven't curved any exams. I only will sort of curve at the end. And what I will do is I'll take a look at the final exam. Typically I adjust the total score on the final exam to something less than the total amount of points. How many points I come down depends. Sometimes it's the high score, sometimes it's just a little bit above the high score. So what I try and do is to not let your grade completely free fall if you don't do well. So in other words, what I try and take a look at is that nobody goes from nobody drops a full letter grade, which would be 3 places, right? I can't guarantee that, but I try not to have the final do that to anybody. If you're on a line right now, you want to do the best. Well, no matter where you're at, you want to do the best you can, right? There's no, it's not like other classes where you have extra bonus points that you can give away to slowly but surely drop down. There is none of that here. So if you're on a line, you want to do the best you can. If you're not on a line, you want to do the best you can. If you're kind of in the middle, then you want to push yourself as high to the next line as you can, in case that line comes down. Don't go down to the bottom, to the next lowest line, because then you don't want that line to creep up on you. It can't creep up on you, but so I mean, and typically I don't, typically if you're passing going into the final, you'll pass. But I think you want more than that, or otherwise you wouldn't be here. You would have been gone at Thanksgiving with a drop. So most people that are in that position don't remain to try their luck, whether they're going to pass or not. But you just want to do the best you can. So I'll take a look at that overall, and then I look at everything overall. I look at the total points, and then I look at percentages, and so I try not to have this affect anybody to the point where you're going to go down, 2/3 or 3, chunks. But if you're on a line, you want to do the best you can, because it is possible you might go down below that line. That's just kind of the way it is. So, and I can tell from, I can correlate how people have done so far to what their scores were on the exam to come up with a rough grading scale for that exam. But this one is my exam, so it's hopefully should be reasonable. But you want to do the best you can. Usually second semesters when you hear I'm not going to bother studying. Okay. Every choice has a consequence. So if your choice is not to study, there will be consequences. But I don't know. I don't believe that, actually. I suppose if you have so many extra bonus points that you can get like a 30% and still get an A. I don't think you should look at things that way. Now I know I was a student pre-spreadsheet where we didn't, where we had to figure all this stuff out by hand, how many points we could get on the final exam and still get our grade. But that's just not the way to approach things. That's like prevent defense in football, right? That never works out well for anybody except the Patriots. So you want to continue to move forward. Don't be defensive. Anything else? Any questions on the selectivities? So your mechanism today would have had 6 steps: the initiation, the propagation, and the 3 termination steps. What I wanted to do was just to kind of wrap up, and there are problems in Wednesday's folder for free radical halogenation. I moved them from where they were before to Wednesday's folder. This was the molecule that you had for the mechanism problem. What I wanted to do was to say, okay, oh, that's right, we still have to talk about the difference in Y. But we'll finish up, we'll talk about, okay, what would be the major product for this methyl cyclohexane with chlorination and bromination, both at room temperature with light, and then what would be the major product if we went above 300 degrees Celsius. So that's the kind of question that you're going to get for on the final is I would give you a molecule and say, here's the conditions, what's the major product? And all of the possible products will be there, I think. There are only 5, there's only 5 choices per answer. I can do more, as you've seen in lab, but there's only 5 choices. But let me just go back to where we were, because we didn't quite finish up the conversation about bromination versus chlorination. So with chlorination, what we said on Wednesday was that chlorination was exothermic. So if we drew out a diagram, we would have our primary radical and our tertiary radical. Because remember, for chlorination, it was 5 to 3.4 to 1. And so we form a tertiary radical 5 times faster than a primary. For bromination, what happened was the step, and this is the step that we're talking about. We're talking about taking the halogen and removing the hydrogen from the carbon to form the HX, HCl, HBr bond along with the radical. That is the rate determining step for free radical halogenation. So for bromination at room temperature, it was 1700 to 80 to 1. And the issue is that step turns out to be endothermic, so that we would still have the primary radical and we would still have the tertiary radical. The question is, why are they so different? Why in chlorination can I form a tertiary radical 5 times faster, but with bromination, I form the radical 1700 times faster? It's the same radical. So what is different about this? What's different is that chlorination is exothermic and bromination is endothermic. So if I'm forming the same radical, there has to be something else. And the exo and endothermic come from looking at the bond dissociation energies, and your book will take you through that if you really, really want to know. But that rate determining step is exothermic and endothermic. So how does that affect the relative rate of forming the tertiary halide? Well, the first thing that we have to remember is that the rate equals A to the minus EA over RT. That is the Reneus equation. So in the Reneus equation, that's what gives us the relationship between rate and activation energy and rate and temperature. So when we learn in general chemistry that the lower the activation energy, the faster the reaction, the higher the temperature, the faster the reaction, it comes from the Reneus equation mathematically. But the key part of the Reneus equation is it's logarithmic. It's a logarithmic function. So small changes in activation energy could have a large effect on the rate. Because the difference between 5 to 1700 seems like a lot. Except if it's logarithmic, it might not be that much. So ultimately, the difference in rate's going to depend on the activation energy for the moment. So if we looked at these two reactions, which one has the lower activation energy? Chlorination, which means chlorination is always going to occur faster than bromination, because overall it has the smaller activation energy. Being endothermic, the activation energy for bromination is much higher. But that's just chlorination is faster than bromination. It doesn't answer the question about why do we form the tertiary radical so much faster relative to the primary radical in bromination versus chlorination. And so in order to do that, we have to remember the idea that Hammond's postulate would tell us that the lower, the more stable radical is going to have a lower activation energy. Okay, great. But now what we have to do is put that activation energy in context of the overall reaction. So because the chlorination activation energy is smaller, at room temperature, the molecules are going to have a lot of energy. Okay. I can go back to my bird analogy that I did when we talked about Hammond's postulate. We do birds or hikers, whatever. The birds, there's three levels of bird energy. There is moderate bird energy, there is supersonic, hypersonic birds, and then there's like birds that are near death that are going to have a hard time going over any mountain because they're so low in energy. Or maybe they're wearing the little cowboy hats like they are in Texas, apparently. Somebody's putting cowboy hats on pigeons, or pigeons are putting their cowboy hats on themselves. That's the bizarre news of the week. But when you're looking at this, so at room temperature with a very small difference in activation energy, yes, the molecules will overcome the smaller activation energy faster than the primary one, but the relative rate's going to be pretty similar. So it's going to be much smaller. The activation energies on a percentage basis are going to be, maybe there's only like a 10% difference there. So when you have molecules at normal room temperature, they're going to overcome each barrier similarly, but still they're going to overcome the tertiary barrier faster than the primary. When we go to a high temperature, what happens? They have more energy. They're going to go over the barriers nearly the same rate because they have lots of energy. So when we go to greater than 300 degrees, I've now given those molecules a ton of energy. They're hypersonic birds. They see two small mountains. They're going to overcome them equally as fast. And so what happens to the relative rates? The relative rates go down to 1 to 1 to 1. They overcome each barrier at nearly the same rate at high temperature. As we go to lower temperature, then to room temperature, they still have a lot more energy. They can overcome both barriers relatively equally, but it's not the same. They're still going to overcome the tertiary one faster, 5 times faster than the primary. If we went to a lower temperature, we could increase that 5 to 1 ratio higher, but at some point the reaction's not going to go. So we can only go so low in temperature before the reaction will stop. So we could increase the selectivity of chlorination by lowering the temperature, because as you lower the temperature, the molecules then have a limited amount of energy. All of a sudden, that difference in those two mountains becomes significant. Right? I have just enough energy to get over that mountain. I'm not going over that mountain. But at room temperature, it's like, I can go over both of them. I'm just going to go over the small mountain faster. Okay. With the bromination, they're bigger mountains with a bigger difference in energy. So now room temperature could be limited energy. So now the molecules would have to take a look and go, okay, now I've got two mountains. I'm definitely going to go over this one faster. I might be able to make it over that one. And now all of a sudden, relatively speaking, we can go over the tertiary mountain 1,700 times faster than the primary mountain. It doesn't take a lot of difference between those two mountains logarithmically to go from 5 to 1 to 1,700 to 1. So room temperature now becomes kind of a limiting condition for those molecules, not simply because this is now an endothermic reaction. But if we go to greater than 300 degrees Celsius, we're back to hypersonic birds, and so they can now overcome equally as well each barrier. And so now the ratio goes down to 1 to 1 to 1. And bromination, if we cooled the reaction down, we would probably hit the no reaction temperature relatively quickly. So chlorination is more reactive than bromination, clearly. But it's the relative differences that are the reason why it's 1,700 to 1 versus 5 to 1. And it's because when you have an exothermic reaction, your activation energies are already small. When you have an endothermic reaction, you have much bigger ones. It means that percentage-wise, the differences are going to be bigger. But again, 1,700 to 1 to 5 to 1 in the logarithmic world is not that big of a change. Okay. So that's the reason why we change the selectivities. In this case is because one's exothermic and one's endothermic. And we could make this reaction really exothermic to the point of explosion by actually reacting the molecule with fluorine. Because fluorine is the most reactive element on the periodic table. The reason we're not doing fluorine is because when fluorine comes in contact with an organic molecule, it explodes. The reaction is so exothermic. Fluorine at room temperature would be 1 to 1 to 1 selectivity because it's exothermic. And fluorine on the periodic table is the most reactive element. If you want to make a noble gas react, like xenon, you react with fluorine to make things like xenon hexafluoride. I mean, fluorine is that reactive. Fluorine was used in the nuclear weapons program in the 40s to make uranium hexafluoride gas. So in order to make the nuclear weapons, they had to enrich the two uranium isotopes. They took the uranium ore, they turned it into uranium hexafluoride, and then they used diffusion to separate out the isotopes that you learn about in general chemistry. They use these centrifuges, right, that often come up with, usually in terms of Iran. Iran has their centrifuges operating. They're not centrifuges like we use. They're ways to enrich uranium. So uranium reacted with the fluorine. The problem was, how do you get the fluorine gas contained? Because fluorine will destroy anything it comes in contact with. Stainless steel, glass. And so they had to use Teflon. The problem was there was no Teflon at the time. It's not like, oh, we'll use Teflon. They had to invent Teflon in order to coat the insides of the stainless steel to keep the fluorine gas from destroying the stainless steel. So Teflon came out of the Manhattan Project, out of the nuclear weapons program, because they had to develop something that fluorine would not react with. And it was Teflon. Teflon is a long chain of carbons with nothing but fluorines attached. It's gone out of vogue in cooking, right? Everybody now buys Teflon-free cooking stuff. But there was a time when it was used to coat. It's still used for skis and stuff like that. So Fluorine's the most reactive. That's automatically 1-to-1. Then bromine, or fluorine, then chlorine, then bromine. Iodine we don't do much with because it's just too unreactive and too slow. It would have the greatest selectivity of all if it would react. So that's the reactivities of fluorine to chlorine to bromine.
You said iodine was the least reactive?
Yeah, it really doesn't react all. Yeah,
Like, I don't know if this is related, but isn't it like the best leaving group in nucleophile?
different reaction. So this is free radical halogenation. And I'm talking, and the iodine I'm talking about is that one, I2. So yes, it is the best, I- is the best nucleophile of the halogens, and it's the best leaving group. But remember that something like I- versus hydroxide, hydroxide wins hands down. So it's strong, I- is strong, but we're talking about a completely different mechanism here. And since you brought that up, that's one of the things that you're going to have to somehow organize is the context of the reagent. So there's a number of reactions with hydrogen peroxide. Right? There's ozanolysis with hydrogen peroxide. There's BH3, hydroboration oxidation with hydrogen peroxide. So some of these reagents you're going to have to put in the context of what it's doing because it does different things under different reaction conditions. So if you go, oh, peroxide, it adds H and OH. Not always. Depends on what it's paired with. So that's the end of the free radical halogenation discussion, except for writing products. Right. So everybody kind of okay with that? All right, real quick, so this is the problem you did today with the mechanism. What would be the major product of this reaction of chlorination? What would be the major product? First thing I have to do is identify the numbers of unique hydrogens that are in this molecule. So I've got a CH3, that's going to be A. I've got a CH, that's going to be B. Okay. In general, always a CH3 is going to give a different product than a CH2. It's going to give a different product than a CH. It's just if you have two CH2s or two CH3s, check and see that they give different named products. So that's the case here. These two CH3, the CH2s that I just labeled C, would give the same product as that one. And this CH2 would give the same product as that one. And then finally the CH2 at the end would give that product. There is a symmetry here. You could think about if there's a mirror plane here, putting a chlorine over here would be the same as putting a chlorine over there, or here, or here. So you can sometimes use a mirror plane to figure out what the major product or what the different products are. I would give you those products. So I would say, okay, here is product one. I'm going to put an X because that X could be bromine or chlorine. There's product A, there's product B. Product C would have off of that. Product D would be off of that one. And then finally product E would be 1,4 to the methyl group. On the exam on the exam now, you'll be given those 5 products. So for chlorination at room temperature, we would run the numbers on each one of these. So we would say, oh, well, product A has 3 hydrogens times a selectivity for a primary position, which would be 1. So A has a 3. B has 1 hydrogen. If it's chlorination at room temperature, that selectivity is 5 because it's tertiary. So it would have a number of 5. So far, B is our major product. C, there's 2 hydrogens here and 2 hydrogens there. So there's a grand total of 4 hydrogens. That's a secondary position. So for chlorination, it would be 3.4, which means we're looking at 13.6. So now C is so far the major product. Then we would go to D, and D has 1, 2, 3, 4 hydrogens that would give its product, its secondary, and so now C and D are tied. When we go to E, it only has 2 hydrogens, it's secondary, so it would be 6.8. And so in this case, running the numbers, product C and D would be the major product of the reaction. So you did just exactly what we did on Wednesday. First you have to identify how many different products there are, and then what is the major product by taking the number of hydrogens and multiplying it by the selectivity of that reaction for primary, for secondary, and for tertiary. Yes?
Are all of the problems going to have a possibility of being more than one answer?
Yes. There's always a possibility of more than one. So this would not make a good problem for the final exam unless I had more than 5 answers possible. So if I did, then what would I do? I would have an F that was like C and D. I might have a G that's like C, D, and E. I'd have different combinations. So I will give you the selectivities so that you'll know you don't have to memorize those. You just have to make sure that when you're looking at the original reactant, you can calculate the number of hydrogens, and then you have to do the math correctly. Which you can use a calculator on if you need to. Under stress, I could see math skills being limited. Of course, if you're under that much stress with these math skills, you might have to manage the other stress of answering the questions. But that's how we would do this. For bromination, if I said, oh, what's the major product for bromination at room temperature? Anybody immediately identify that one? B. So for bromination, if there's a tertiary position, because it's 1700 to 1, I don't care how many hydrogens are there. So for bromination always goes tertiary. And if there's no tertiary position, then it's going to go to the most populated secondary position. So in this case, that product B would be 1700. And then if we if we went to either one of those at greater than 300 degrees Celsius, now I'm just based totally on the number of hydrogens because I'm at 1 to 1 to 1. So now I would say, okay, Who's got the most hydrogens? And when I look down this list, I see C and D both have 4 hydrogens, so they would be the major products. And so there are more of these problems in the folder on Wednesday, and I think there's narrated answer keys that go with them, but there are also these problems on the problem set that's in the last folder, Grace.
So at 300 degrees C or greater than that, it would be C and D for both chlorination and bromination.
Yes. The difference between, you would get C and D as the major product if you do this at greater than 300 or at chlorination at room temperature. The difference would be the percentages. And you could calculate which one you would get a greater percentage of C and D with. But chlorinating this molecule, you're going to get a mess of products unless you brominated it. And if you brominated it, that's going to give you the highest percentage of a major product, simply by the numbers. Okay. Any questions? I don't think I gave you any time to ask questions about other things, but you can put them up on Piazza. You can come and see me. Email me if you want a private answer, I guess. But otherwise, that's where we end off for the final. Okay?